Example 3. Analyze the graph of r of x equals x squared plus 3x minus 10 over x squared plus 8x plus 15. So first we want to look at the domain of this rational function. So when we want our domain, remember we're looking for values of the that make the denominator 0. So let's factor our denominator. So this will factor x plus 5 times x plus 3. Oops. So we know that any zeros of the denominator will cause the function to be undefined, so we can see the zeros of the denominator are -5 and -3. So the domain is going to be the set of x's such that x does not equal -5 or -3. Step 2, we want to see if we have any holes in the graph of this function. So to do that, we have to look for common factors in the numerator and denominator. So we'll also need to factor the numerator of this function. So we've got a trinomial. We'll do our trial and error here. And this will factor into x plus 5 times x minus 2. So we see that we do have a common factor of x plus 5. So we're going to reduce this function, but that common factor means that there is a hole when x plus 5 equals 0. So we set this to 0, so we can see there's going to be a hole when x is -5. So that's the x value. And now once this is reduced, we've got x minus 2 over x plus 3. We now need to evaluate to find the y value of that hole. We have to graph an x and a y pair, not just the x value. So we'll find r of -5. So we'll plug that into our function, -5 minus 2 over -5 plus 3. So we'll get 7/2. So we know we have a hole at -5, 7/2. Now we want our intercepts. So we know for our x-intercepts, we look for zeros of the numerator, because anything that makes the numerator 0 will make the entire function equal to 0. So we can see the 0 of the numerator is 2. So if x minus 2 is 0, so we're going to see we have an x-intercept at 2. Now for our y-intercept, we'll evaluate the function when our x value is 0, so we want r of 0. So 0 minus 2 over 0 plus 3 gives us -2/3. So we have our y-intercept of -2/3. So if we write these as ordered pairs, 2, 0, and 0, -2/3. Now our vertical asymptote. Once the function's reduced to lowest terms, once we reduce that common factor, remember that common factor of the x plus 5 tells us there's a hole at x equals -5. Once it's reduced to lowest terms, any zeros of the denominator now indicate vertical asymptotes. So if I take x plus 3 and set it to 0, I get an x value of -3. So that means we have a vertical asymptote at x equals -3. Now we want to see if we have horizontal or oblique asymptotes or neither. So we want to compare the degree of the numerator and the degree of the denominator. So whether you look at the original function or the reduced function, it's the same as far as the degrees. The degree of the numerator is the same as the degree of the denominator. So when they're the same, we know we have a horizontal asymptote. So if you want to make a note, that's because the degree of the denominator equals the degree of the numerator. And remember, to find the equation of that horizontal asymptote, we take the leading coefficients. So again, whether you look at the original functions or the lowest terms, the one that's reduced to lowest terms, you still have the same coefficients in front of the leading terms. So we divide those leading coefficients. So if we divide the numerator's leading coefficient, which is 1, and the denominator's, which is 1, we get a 1. So we have a horizontal asymptote when y is 1. Now we want to check if our graph intersects that horizontal asymptote, because remember, these rational functions, the graphs can intersect horizontal or oblique potentially, but they cannot intersect vertical. So we'll set our function equal to our y value of our horizontal asymptote. So I'm going to set my function equal to 1. So if we solve the equation, 1 equals x minus 2 over x plus 3. So we can cross multiply here, and we'll get x plus 3 equals x minus 2. If we subtract x from both sides, we're going to just be left with 3 equals -2. So obviously there's no solution to that equation. So that means there's no intersection. So this graph will not intersect its horizontal asymptote. Now let's look at the graph on the calculator. When we enter the function, remember we need the entire numerator in parentheses and the entire denominator in parentheses. If I graph on a standard viewing window, zoom 6, zoom standard, okay, so we can see 2 branches. We can see a vertical split here, and that certainly looks like it could be a -3, which is our vertical asymptote that we found. We can see a horizontal split here, and that certainly looks like it could be about a y value of 1. And let's actually look at the table. So if we look at the table, we have an error at -5 and an error at -3. Well, that -5 makes sense because remember, that's the location of the hole. That was the common factor in the numerator and denominator, the x plus 5. So there's actually a hole there, so that makes sense why there's an error. And we also have an error at -3, which also makes sense since we have a vertical asymptote at x equals -3. Okay, so let's make our sketch of our graph. We know we have to at least go over to -5 on the x-axis because we have got a hole over there at -5. Okay, so I always think it's a good idea to start with the asymptotes because that kind of gives you a boundary, a grid for you to fill in your shape. So we have a vertical asymptote at x equals -3. And we've got a horizontal asymptote at y equals 1. We have our intercepts, so we have a y-intercept at -2/3. We'll approximate that here. So here's 0, -2/3. And then we have an x-intercept at 2. So here's 2, 0. So we can already see, if we look at our grid, oh, and we forgot our hole. If we graph the hole, 1, 2, 3, 4, 5, -5, and then 7 halves, 3.5. So maybe up here. And instead of a hole, or sorry, instead of a filled-in circle, we're going to draw an open circle for a hole, kind of like we did on the piecewise functions. And so this is at -5, 7 halves. So just from the points that we found above, the hole and the intercepts, we can sketch the shape of this, which we can also confirm from the calculator. So remember, when we've got this grid, it's split into 1, 2, 3, 4 parts here, 4 quadrants. We have a hole up here, so we know our branch has to be above this asymptote. Remember, we're not crossing the horizontal asymptote. We found that. So we're going to draw our branch approaching those asymptotes, and I can actually extend this a little bit bigger so we can see that better. And then we can clearly see we have a branch on the right side of our vertical asymptote. Instead of a branch above the horizontal asymptote, we'll have a branch below. Remember, we can't have a branch above and below here because that would fail the vertical line test. So just sketch your shape, that ramp branch looking shape. Just sketch it so it looks like you're approaching those asymptotes without actually crossing them. Now we have our graph, so we can describe the end behavior of this function. So as I trace to the right, as my x gets larger and larger on the right end of the graph, my function is flattening out. It's approaching a y value of 1. That's because of that horizontal asymptote. So we can say, as x approaches positive infinity, r of x is approaching 1. Then if we trace along our left branch, again, we're flattening out. That y value is approaching that y value of 1 at the horizontal asymptote. So as x approaches negative infinity, r of x also approaches 1. And then finally, our behavior around the vertical asymptote. So here's our vertical split. We've got a branch on the left and the right. On the left branch, as we trace along, we skip here, there's actually a hole punched out, and then we trace along, that y value is getting larger and larger and larger, but never crossing that boomerang shape, that ramp shape never crosses the vertical asymptote. So we can say as x approaches -3 from the left side, with that negative superscript, r of x approaches infinity. And then if we look at the branch that's to the right of our vertical asymptote, as we trace along it, our y value is getting smaller and smaller. So we can say as x approaches -3 from the positive side, r of x approaches negative infinity.